E dalle altre sezioni, non so se ci vedete, ci sentite?
C'è sfarfallio.
Sì. Strano, non intendo adesso. Lo sfarfallio non so se dipende dalla lampada che sta o da qualche altra cosa.
Sistema il cavo.
Quale?
Quello che collega il computer.
Io ho paura di toccare cavo qua.
No, l'abbiamo staccato ieri, stava attaccato al mio computer. Questa cosa è semplicemente questo che non ha visto bene.
No, però devo fare uguale. Devo fare la stessa cosa. Vabbè, facciamo così.
Molti stanno collegati.
Sì, grazie. Sì.
Troppo brutto, ne sono mezza vuota, però...
No, anzi, sinceramente.
E penso che forse possiamo iniziare. Okay, so lo dico in inglese, so dear colleagues, we are really happy today to have the pleasure and the honor to have with us Professor Lambeck at the INGV. This is not the first time he's here, but we are really happy and proud of this. Kurt is a retired professor of geophysics at the Australian National University in Canberra, Australia, and he had several positions during his career. He worked at several European and American research centers and universities, and also is an associated professor researcher at INGV from a few months. And because he collaborates with us since 2003 regarding sea level changes in the Mediterranean. And during his career, he received several awards and honors, like the Order of Australia, the National Mediterranean France, and in 2012 has been appointed by the past president Giorgio Napolitano as the title of Knight of the Italian Republic as the winner of the Balsam Prize. So, joking with Kurt, he said that he is like Berlusconi. His research interests are on geophysical geodesy. He wrote a very useful book. It's called Geophysical Geodesy, which is like a Bible for us geophysicists. And his interests include the interaction between the oceans and the atmosphere with the solid earth, and sea level changes and the glacial history, and the archaeological implication in the Mediterranean region. So today, Kurt has a very interesting seminar entitled "The Mantle, Viscosity and Ice Sheets: What can we learn from glacial rebound studies?" Or are these elephants in the room? So I don't know if you have elephants in the room. Maybe.
Well,
Thank you, Kurt.
Then I've plumbed the depths of my Italian, so I'm going to have to speak in English, unfortunately. I have to come back a bit more often and spend some time trying to learn it. In English, we have an expression, is there an elephant in the room, which means, are there questions that we all know exist, but nobody wants to address them? And that's really what I'm going to try and do in my presentation today. What do people say about the mantle viscosity, as we infer from the glacial rebound problem. But what are the real problems that nobody really wants to talk about? So that's what I'm going to try and do. Now, this is not going to be a very polished seminar. I only finished preparing it about 2 minutes ago, and I haven't prepared to do anything. And a lot of the later work is work in progress. So if I do not provide all the answers, at least I hope we go away understanding why we cannot necessarily give the answers at this stage and what are the real limitations of the our knowledge of the Earth's viscosity. So that's what I'm going to try and do. Now, the reason the problem's important is there are several reasons in the earth sciences, and in a sense, the study of the glacial isostatic adjustment, as we call it, the GIA, covers many parts of the earth sciences. When we talk about vertical tectonics in the geological literature, we are usually referring to measurements that are made with respect to sea level. So if sea level is going up and down for other reasons, then we need to know that if we want to get good geological estimates. Then for geophysics, of course, this GIA problem is a classic problem. It goes back almost 100 years of people trying to estimate the mantle viscosity from our observations of the rebound underneath the large ice sheets. And we need to know that rheology, of course, if we want to understand mantle convection, if we want to know the thermal history of the planet, and so forth. So it's a very critical observation. For geodesy, it's important because these past processes are still going on today, although at a much lower rate, of course. And if we want to get precise positioning, precise gravity measurements, precise satellite movements, we need to know what these isostatic contributions are. So they're sort of nuisance observations, if you like, from the geodesists that we want to strip off. And that becomes particularly important and difficult today because the GIA signals are quite small and they become comparable to many of the environmental signals that people are trying to estimate from the geodetic observations. For example, if we want to know what the effect of the melting of Greenland on sea level is today due to present-day melting, we need to know the past geological signal, otherwise we cannot say anything about the modern signal. For glaciology, it's important, and I'll talk a bit more about that as we go along, because we know where the ice sheets were, more or less, but we don't know really independently how thick the ice was, where it was, and the rates at which it melted. So the sea level, as I've said already, a sort of perturbation, the background signal to understand modern day relations. And for climatology, it also becomes important when we go further back in time. As we go beyond the current glacial cycle, we use the oxygen isotope records to look at what the sea level has been doing, what the climate has been doing, but we need to calibrate that isotope record, and we do that by comparing it with the more recent data. And if we can do all these things, we can then begin to reconstruct what the planet would have looked like back in time and start addressing archaeological and prehistory questions. There are lots and lots of things we can do with it once we understand the problem and once we have a predictive model. So the challenge really is to try and develop predictive models based on physical principles that provide a realistic description of that Earth, ice, ocean system during the glacial cycles. And the question really, that's what we want to do, and the question really is, do we have the information that allows us to do that, to address the questions in these various fields? And if we don't have it, what are the unresolved issues? Now, we do that through the process of geophysical modeling, and I think I'm in the community here that understands modeling. This is more for the benefit of the geological community, because they will always dismiss what we do and say, oh, you're just modelers, you just model away. And I try to point out that what they do is modeling as well, just of a different kind. But the modeling that I do is very much in the spirit of these two quotations here. It's not so much to provide, to say, look, these observations are described by this model, but it's to try and sharpen the questions, to try and learn more about the physics of the problem. And then keeping in mind that models will always be wrong. And the question really is, how wrong do they have to be for them not to be useful anymore? So that's the basic philosophy of my modeling. And you will see that my inversion processes are not the most sophisticated processes that a lot of geophysicists use. They are simpler ones, but they work extremely well, and they give me a better insight into the results I produce than the complex models do. And that's a reflection on me, not on the modeling necessarily. So let's ask, what are some of the questions? Let's start with the rheology, because I think that's probably what most of you will be most interested in. And the sort of questions we want to ask really, what is the depth dependence of the mantle viscosity? What are the gradients of the viscosity? Where do the discontinuities occur? And the other important question, of course, is this viscosity linear or non-linear? Is there a transient pre-process going on or not? Can we say anything about that? And the important question, of course, is what are the lateral variations? As I will show in a moment, most of the work, nearly all of the work that's been done has assumed that there's no lateral variation. And then there's a question which I put down here for Carlo's benefit to a large extent, because he's asked me this question on at least two occasions. Can we say anything about anisotropy in the mantle from the viscosity, from this rebound analysis? And I'll try and say a few things about most of those issues. The first one I'll address is the depth dependence of viscosity. Despite this probably being the most elementary part of our viscosity model that we want to know, there's still a lot of divergence in the literature on what the realistic radial profiles of the average mantle viscosity would look like. And I'll illustrate that with essentially simple models in the first instance, the Maxwell models, a linear viscoelastic model. Use that as a starting model, and then you can ask the questions later, is this sufficient or not? It doesn't mean that the Earth is linear. I mean, if the Maxwell models work, it doesn't mean that the Earth's rheology is linear, but it means that the parameters we estimate describe this particular phenomena. And the real challenge then becomes, how do we interpret our effective viscosity parameters that we get from this work to the real physics of the mantle? That's a real difficult and separate study. So what we do in the first instance, we take a mantle model, the schematic viscosity profile based on typically mainly on thermal considerations and any seismic evidence, and we model that as a series of layers which have elastic parameters that are constrained by the seismic data, the density elastic moduli, and in which the viscosities are defined by layers of a viscous element with its elastic components. And then we put the ice sheet on it, and then we see how this system responds. And some of the results that have been obtained over the years, there's some earlier results here. The pointer or is that a pointer?
I think you can have a pointer.
Okay. The far one is a simple model, a three-layer model, lithosphere, upper mantle, lower mantle. That's the one that we've used most of the time, and that seems to work well for many of the problems. And the essential feature is a viscosity contrast of almost 2 orders of magnitude between the average effective viscosity for the upper mantle and the lower mantle. It's only in one case where we find convincing evidence that there may be some layering in that upper layer, and that's for the small ice sheet of the British Isles. And I'll come back to that in a moment. But if I represent that rebound for British Isles with this model, it'll work just about as well as it does with the more realistic model. And that just shows straight away that the resolution we have from the inversions is limited, and it's dependent to some extent on the extent of ice sheets. Small ice sheet stresses the upper mantle, the big ice sheet stresses the entire mantle. And by using ice sheets of different sizes, you would hope to be able to find some greater depth dependence. This is a model from Forte and Trivica at about the same time, and they produced a much more complicated structure. And these are some models in their revised solutions that are all quite different. And in many ways, these models fit the data about as well as that one. So that becomes a good operational model, and then we try to understand what the detailed structure may look like. So that's one knot. This is a model of Peltier, the more recent one, this black line here. You see it's quite a different one. The average mantle viscosity is much less than 10 to the 22, and the lower mantle viscosity is about 10 to the 21. Very different from the results that I'm getting, that I've been getting for a long time, and been arguing is a better model. And in their publications, they never mention our results. But recently, I can't resist putting this quote in here from the paper of Lau and colleagues from Trivica's group, where he's looked at all of these models very carefully, and he concludes that the conclusions really are the ones that we drew already some 20 years ago are still the appropriate models to use. So that's something. So the essential point there is there's a lot of variability, and I'll try and address in a moment. Can we do any better than that? The next question I just need to touch upon briefly, are these maximal models valid, or should we be considering more complex models, for example, Berger type model with several time-dependent viscosity constants, or a nonlinear model? And unfortunately, the data that we have doesn't permit us to really address that issue. The one thing we've tried to do is to separate out the geological observations from the geodetic observations. I don't combine the two types into one solution if I can avoid it. And the reason is that the geological data generally is from the period from the ice first retreated, say about 15,000 years ago, and most of it up till about 6,000 or 7,000 years ago. So it's data that refers to a period where the stresses, the relaxation process was rapid, whereas the geodetic data, it's sort of 10,000, 15,000 years after the end of the deglaciation, after the end of most of the deglaciation, and the stress levels are much lower. So I figured that there's the possibility that we would see different viscosity estimates depending on the time period that we're looking at. So we've tried to do the inversions, and again, I'll come back to some of this later, using the geological data and then using geodetic data for the same region. And the only place where we can do this with any confidence is for Scandinavia, where both data sets are very high quality and sort of homogeneous. And what we essentially see, this is for a three-layer model, a simple model again, next slide. But essentially what we see, the lithosphere, whether it's geological data or the tide gauge data, these two are the geodetic data sets. There's no difference there. The upper mantle, the lower mantle, in all cases, the mantle below about 670 kilometers, is pretty indeterminate. Again, it's something I'll touch on in a moment. And the one possible difference is between in the upper mantle, the average upper mantle viscosity, where the geological solution tends to be lower than the geodetic solutions. And these uncertainties are all sort of 2 sigma type estimates, 95% probability. And if you statistics don't have a great meaning here because we don't really know the distribution of the observations. We don't know what the real statistical properties of the data are, so they're pretty rough estimates. But personally, I think they're fairly realistic, because if I use these viscosities here and look at good predictions for the geological data, I don't get a very good agreement. So there's a suggestion here that something is going on, that when we look at data in different time scales, that the system may not be entirely linear. And that's something that we need to pursue further. And I think that can come about in the future if we have better geodetic data for, say, North America, and if we can get better geological data sets for North America. We'll see, perhaps touch on that a little later. The other question that we need to ask is, what about the lateral variation? I think we all know that from the geophysical knowledge we've known for decades, lateral temperature variations, lateral variations in the composition of lithospheric crusts, or continental lithosphere, oceanic lithosphere, etc. And we should be very surprised if we didn't find lateral variation. Yet nearly all solutions, as I said earlier on, have assumed that it's not important. The reason why that's been mainly assumed is that numerical expediency is much easier, of course. 3D models are only now beginning to appear, but none have yet been applied on a large enough scale, largely because the real question is, do we have good observational evidence to solve for lateral variation on a global scale? And I'll address that a bit later in a bit more detail using regional models and show that lateral variation is indeed significant. And this is just an example of why we expect it. This is the calculation of Priestley and Mackenzie based on thermal and petrological arguments, where he argues for an uppermost mantle layer of high viscosity underneath the continent and much lower ones underneath the oceans. The only trouble with this prediction is that the contrast between these upper mantle continental value and oceanic values is about 3 orders of magnitude. And I'm in a long discussion with him at the moment to try and understand this, because if that is correct, then everything in the ocean environment will be locally isostatically compensated. Whatever problem you look at, you'll never see evidence for anything other than that, because the time scales for the relaxation become so short. And that's totally inconsistent with the data. So I think the relationships between temperatures and the mineral physics, I suspect, are more complex than his models allow for. And that's something I've got to try and convince Dan of. And we already had some earlier results in 2001 that led us to postulate that there was lateral variation in the upper parts of the mantle from the GIA analysis, particularly with atmospheric thickness, effective thicknesses of about 50 kilometers underneath the Pacific to something like 100 kilometers under North America, for example, and a progressively increasing mantle viscosity as you go from the ocean environments to continental margin environments to the Scandinavian mantle and to the North American upper mantle. And you see that the differences are fairly small. They're not the 2 or 3 orders of magnitude that the minimal physics would lead us to suppose. The lower mantle, I can't really say much about. We'll see a bit later again some of the resolutions for our solutions. We really can't say a great deal about lateral variation, and all I can say is a little bit about possible layering in that, and I'll show some results in a moment. So that's sort of in a sense where on the anisotropy part, I have no results for this other than a very simple observation, and that is when I analyze the radial GPS data for say for Scandinavia or for North America and estimate the viscosity, then I get different value, and I do the same thing for the horizontal displacements. There's a horizontal component to the radial, to the GIA. When I do that, I get different values. They're not consistent. The problem at the moment I see is how to solve the reference frame issues in the GPS. There is a GPS, there is a reference frame problem there. I can't go into that now. It's complicated and takes some time. And that sort of needs to be resolved. We need to find a way of analyzing the GPS data that is independent of a reference frame, of a GPS reference frame, a reference frame that is itself perturbed by the GIA data. So it's a sort of circular, you risk running into a circular situation. But it's an interesting avenue that I think needs to be explored, and that may lead us to some answers to the question of potential anisotropic behavior of the viscosity. So to take, that's sort of roughly where the situation stands or stood, say, until recent times. And to try and take it further, we have to address a number of issues carefully. We have to address this question of what is the appropriate Earth rheology representation. There are some issues remaining in how we define our surface loads, because what we're measuring is the Earth's response to a surface load, and there are some questions we need to address. I'll touch on that in a moment. And we need to look much more carefully at our observational data than is often the case. And in particular, we need to look not just at its precision, we need to know what its real accuracy is, what its reliability is. And again, time doesn't permit me to go into any detail on that, but I just emphasize that it becomes very important to have a very good understanding of the observational data. A lot of analyses just take somebody's geological data without questioning, put it on their Earth model, then somebody else's ice sheets, and they get values for the viscosity. And I think when you do that without considering these other issues, you're likely to be misled. So what comes up next? So let's just make a couple of comments about the surface load definition. When we talk about the glacial isostatic one, we talk obviously about the changing ice sheet, but we also have to talk about where does that meltwater go when the ice sheet melts, how is it distributed into the ocean, and what is the consequence of that redistribution on the Earth itself. Because that water load will stress the Earth as well. And that's been very well developed already back in 1972 by Farrell and Clark, a formulation that ensures that the ocean ice mass is conserved. The amount of ice, the mass of the ice going into the ocean is equal to the mass and the change in the ocean, and that the ocean surface remains an equipotential surface throughout time. That means it's got to take into account the changing gravitational attraction between the ice and the water itself, and also the changing gravitational attraction of the deforming Earth, the internal deformation and the surface deformation. But there are a few questions that weren't included in the original formulation. This is sort of second order effects, but they are becoming important today, I think. If we want to address some of the issues that I've raised, we need to take these into account. One of them is that we need to take cognizance of the fact that coastlines, the coastlines themselves are changing with time. But as the sea level rises, the coastlines globally or in many parts of the world will advance, or they will, in the glaciated regions, they will retreat. So the coastlines become a function of time. But the height of the water column at each point on the Earth's surface also becomes a function of time. And that's really the quantity we need to know. What is the height of that water column through time? So we need a complex formulation. Obviously, it's going to be an iterative procedure to model that. Another something that we need to think about is how much of the meltwater is actually stored on the continents for a period. And we have these large, and I'll show an example in a moment, these large glacial lakes that have formed on the edges of the ice sheet in North America, for example, and particularly Eurasia, and do they make a contribution? And then we need to ask ourselves what happens to the ice sheets when they are sitting on the current shelves. So we need to know the grounding line, because if you're within the grounding line, then it represents a load. If you're looking at what's essentially floating ice, then it's not a load. So you need to know what the grounding line of the ice sheets are doing through time. And the current formulations take those into consideration. And the main consequence is that it takes a calculation. It used to take 10 minutes to do on a particular process, and now it takes about 10 times as long to do. And when you do a lot of modeling, it becomes expensive to do, but it's worth doing. And that's so essentially what we need to do. We define the function which we call the equivalent sea level, which is the average global sea level on the globe as a whole. It should be 0, but it's going to be a function of the water depth column integrated over the. It's a change in that, of course, we need between the water depth at time t, the area of the ocean at time t, minus the depth, present-day depth in the area. So that gives you a measure of the change in the ocean volume, and that has to equal the change in the ice volume given by the amount of ice that melts converted to water needs to equal that. So we won't bother about the details there, but you get the picture. And I'll try to illustrate in this messy, sort of quickly drawn figure what the situation is at the where the ice sheets comes onto the continental margin. Take this lower part here below the green line, dividing line, and let's take this as the present situation. We've got the land surface here. We've got an ice sheet sitting here. This could be Antarctica or Greenland, for example, and we've got the sea level here. The load we have to calculate is this height of the water column everywhere over the oceans, including on the shelves here, right up to the grounding line of the ice. And the present-day ice load is simply the difference between the ice surface and the topography. And then back in time, this surface will have deformed because of the glacial rebound, so you have a slightly different surface. And the ice may be now on the shelves, floating off here. And what the ocean load is effectively from the ground line, it's all that area here, and the ice load becomes all of that here. And there would be a lot of ice sitting on the shelf. And then the ocean area in the past would be this one, and the present-day ocean area would be that one. And that's what you've got to keep track of in our models throughout time. So it gets a complex sort of business. But this is an example of these pro-glacial lakes I mentioned, a reconstruction of it. This is for stage 5A, one of the early cold periods when you had a large ice sheet over the Barents and the Barents Sea, with the northern part of Russia, and it dammed the north of flowing rivers, directed the waters to the south, and it predicts, this is a model prediction, it predicts that it flows over through about past into the Aral Sea, the Caspian Sea, and the Black Sea, and into the Mediterranean. And likewise, the White Sea expands and goes into Volga, and that sort of thing. But the weight of that, these water depths can be up to several hundred meters, and they impact on the rebound of, say, along the edge of the Urals. And we see evidence for that rebound and that along here in delta systems, and the rivers that flow into these lakes from the Urals, for example. And that becomes a very valuable observation to test these models. And that's sort of interaction between the topography, the drainage is something that needs to go into the models. The other well-known example is the Baltic, which appears is isolated from the Atlantic Ocean, and that adds to the load that we need in the description. Now, let's assume that we got these things straight, that we got the computational procedures right, and I won't guarantee them 100%, but I think I'll guarantee them 99%. We have to ask ourselves, we need to know the ice sheet. We can't just take an ice sheet from somewhere and put it on the Earth and expect to get realistic results. This is an old sort of reconstruction of Benton Hughes, but it serves the purpose. It shows the limits of the ice sheet at the time of the last glacial maximum. And in this particular model, based very much on the earlier Russian interpretations, they have a very large ice sheet sitting over here at Kara, similar to the one I showed a moment ago from stage 5D. If that is really there, then we would expect to see isostatic rebound along the present-day coast that would be similar to the Norwegian coast, for example. So simply by knowing what's happened, it allows you to say something about the potential magnitude of these things. But that's a certain uncertainty. The question of the ice over the North Sea is an uncertainty, and that would impact on the observations on the Norwegian coast and in Scotland, for example. The question of the Cordilleran ice sheet is still a largely unresolved one. We do not really have a satisfactory model of how much ice there was in that particular ice sheet. And the other big unknown is not shown here is in Antarctica. What do we know about the Antarctic ice sheet in the past? And the answer very simply is very little. And if that is so, is that going to impact on our geodetic GIA corrections, etc.? Another question that has arisen in the geological literature is that whether the ice sheets extend far off the present-day coast. There's a whole body of literature that says that the ice only came as far roughly as the present-day coastline, and it didn't go onto the shelves in the past, and that would be true for the coast along here. This is Benton and Hughes took another one, they had it going out from those places. And the evidence for that has mostly come from the cosmogenic dating, where they've got old, I think it's mainly beryllium ages of the rock exposures. And they say that, therefore, it could not have been ice covered. But if that is so, then you can test this very quickly with the GIA models. This is an example of a fairly old one now, it's now from Spitsbergen, where the observations, this is Svalbard is on one side and North Atlantic on the other side, and this is the side sitting right on the coast, present-day coast on the island of West Spitsbergen. And the observations we see is a falling sea level starting at about 11,000 to 12,000 years ago. This is when the area first became ice-free, so it's made all the information falling through the slight oscillation and going down to the present. But if the ice was restricted to the continent, to the present-day island, then the prediction looks something like that. We are in an area here where for that early period, all the evidence should be below sea level. So either you have to suppose that there's been a lot of tectonic uplift, or you have to suppose that the ice sheet came out onto the continental shelf. And wherever we really look on the coastline, whether it's Labrador, we've been doing field work in southern Greenland, for example, we always see similar sea level curves of this nature. And in the one location in Antarctica, the Westport Hills, where we have a good geological record of sea level for about the last 8,000 years, we see similar sort of behavior. And that leads me to conclude that in the majority of cases, when the ice sheets, during the LGM, the last glacial maximum, the ice sheets generally extended out to the edge of the shelves. And that creates a problem for the glaciological community, although I think nowadays they're beginning to accept that interpretation, which is encouraging. But it's the sort of thing we can do already with fairly simple models, at least get the magnitudes. That's another example of that, exactly the same problem. No? Okay, this is a bit out of place. So just a couple of comments about the observations, the justification really for what I did mention early on about separating them out. The present-day geodetic data, lots of sorts of data, very precise, but long after the main deformation events occur. The geological data, generally less precise, but much closer to the main events. So the two are complementary, and that's important. And then the archaeological data is sort of generally on intermediate timescales, particularly in the case of the Mediterranean, where there's a growing body of information from archaeology as to where sea levels were at about 2,000 years ago, at a time when the resolution of the geological data is no longer very good. So that becomes an important data set, and that's in fact the reason why I'm in Rome today to pursue that particular area. And there's another reason, and that becomes important for geophysics, as I'll discuss at the end. So again, to come to what the real problem is, we've got, I haven't said how disparate they are, but the observations are of different types, different reliabilities, they measure different things. We have other things going on, for example, the environmental signals, deforming, loading the Earth, contributing to the geodetic measurements in particular, and can we then develop a useful predictive model that enables us to say something, what are going to be the deformations from the GIA process alone into the future, what are going to be the sea level changes in the future if the current ice sheets continue to melt. Because if we understand the past problem, we should be able to make predictions for the future. So the way, and I think we can address a lot of those issues, I think we can make progress despite that may seem a negative sort of statement. And we do that by taking advantage of a couple of features of the GIA signals, we have this sea level equation, this Farrell and Clark equation with all these complexities added to it, which essentially says that the relative sea level at a particular point in time, this particular location, is equal to this ice volume or its equivalent sea level, which is a measure of the total ice in the system, the total change in ice in the system is a function of time. And we have the two isostatic responses, one from the change in ice loads and one from the change in water loads. And the ice load term is primarily the function of the ice sheet, in particular the details of the ice sheet, and a function primarily of the earth rheology beneath the ice sheet, and that will be varied at space and time. Whereas the water term is a function of the total ice. This is some of the ice for a particular region. This is some of the total ice. The earth rheology essentially in the under the water changing water load will be a function of the total change in the water load at that site, because that determines the height of the water column. Changing water column, that will be a function of position and time. And then, of course, there's any tectonic and environmental contamination that you can have. Just one quick word I'll make about that. Our analyses, if we are not interested in the tectonics in the first instance, our analyses try to avoid any area where there's evidence of tectonic movements, and use the elevation of the shorelines during the earlier interglacials as we can, absence of seismicity, some standard geological arguments of stability, etc. We try to avoid, emphasize try, tectonic contamination, but there'll always be some present, and that will always add noise to the system. That's pretty well impossible to model. Then what we do is we divide the observational database up into two parts, to what we call the near field. These are the areas beneath the former ice sheets. These are the areas where the main response is a rebound to the melting ice. And that produces primarily this signal here, here. And then the second area is a far field, this area far away from the ice sheet, where the main change in the load is the water load. It's water from the ice sheet goes globally into the oceans. This margin, for example, is being loaded by water in the South Pacific, and it's responding to that. And it's primarily, and the dominant terms there is the ESL term, the ice volume term, and the effect of the water. And this term will be a function of the rheology beneath the loading area primarily, but they will not be sensitive to the details of the ice sheet, whereas this one here is sensitive to the details of the ice sheet. So you can see the strategy. You look at the data from here to get the details of each ice sheet and the rheology underneath the ice sheet. We look at this here to get an estimate of the total change in ice volume and the rheology underneath the oceans and continental margins where most of the data is located. And then you have the condition, of course, that this total ice volume that comes from this analysis must equal the sum of all the near field analyses for all the ice sheets. So we have a constraint on that. So that's the essential strategy that we've developed over the years, and it seems to work very well. And what it provides us is not a global solution, but it provides us with regional solutions for different parts of the world. And what we try to do is then to, when we have these, to cobble them together really, and then get a global picture, but we're not quite there yet, for a reason that should be clear by now. This is just an illustration, a calculation of the displacement in the mantle. This partly justifies our approach. This is going from the North Pole to the South Pole, from the surface of the Earth down to the core mantle boundary. And we plotted up here the direction of displacements. In this case, it's 10,000 years after the unloading of an ice sheet. That was the dimension of the Laurentide ice sheet, so it's statically something like that. And the scale of the displacements you see here is another linear scale. And clearly what you see that most of the deformation is restricted fairly closely to the area that was ice loaded. The displacements out here are very much smaller. In other words, observations here are going to be dominated by this part of the mantle. Observations out here are going to be dominated by the mantle underneath the oceans. And that's sort of our justification really for doing what we do and for drawing the final conclusion that I'll draw in a moment. That one is for a North American ice sheet, which has an extent of about a radius of about 1,500 kilometers. The area of extent that's comparable to the distance from the surface to the mantle. And if I go to the kind of Scandian ice sheet, what have I done? Sorry, that's the North American one, and this is the Scandinavian ice sheet. And what you see there, a similar situation. It's confined to the area not far from the ice, former ice margin, but most of it is concentrated in the upper mantle. So my concept was that this ice sheet should tell us something about the upper mantle mostly, whereas the other one, the larger ice sheet, will tell us a bit more about the mantle here as well as down here. And if I look at the British ice sheet model, which is a tiny one, something like this, I see that it only really stresses that part of the mantle. The figure I have for that, for some reason, doesn't show anything. It's so small, I think. So schematically, this is what we do. We go through a complex circle of calculations. We start off with some sort of Earth and ice model. We have a set of observations, and we will try to estimate the viscosity, the ice volumes, and the viscosity structure, the ice parameters, and the Earth parameters. And I'll take the far field data from the ice sheets, and as I've said, this is primarily a function of the total ocean volume and the Earth parameters for that region, and we invert the observations to get some preliminary values or preliminary values for that region. And then we will iterate a few times. Normally, in the process, ask ourselves, are there critical observations missing? Are there areas that we need to go to get new data? And that's one of the things we've done. We come to the islands in the Pacific, for example, in the Indian Ocean, to look for data that we think will answer specific questions. And then in parallel, we do the solutions for each one of the ice sheets. We collect the observations from those areas, do the inversion for the local changes in ice volume, distribution in the ice, and meteorology there. And so that. Then in principle, if we've been successful, this volume here in the last iteration should equal the sum of all the individual ice volumes. If the answer is yes, then we've got a good predictive model. If the answer is no, then we ask ourselves, what is the nature of that discrepancy and how do we deal with that? How can we, if there's too much ice in the individual ice sheets, where can we reduce it? Or if there's not enough, then we ask ourselves, where can we put it? And we go through the whole cycle again and again and again. And it's been a combination of these, going through these cycles and doing field work that has dragged the whole program out. The far field database, for example, our recent 2014 solution, all the green points show us areas where we have observations that I think are reliable and observations that we understand. There's one point missing, a bit unfortunate, that's the Barbados one, that should be able to stuff in there as well. And that forms a database for the far-field solution. So this, if I take all of that data and just plot it up, nothing done to it, then I get a curve like that, which is a sort of pretty representative sea level curve, but there's quite a lot of noise in it, if you like. It's a fairly broad band. You've got the glacial maximum, you're coming into it here from stage 3 at about 30,000 years ago. Could do things here, I don't know. Rises, you see how little oscillations, and the reaches present about 7,000 and drops off to the present. And if you're only interested in sea level curvature within a 10 meter shape, that is quite sufficient. But when you do the inversion, you check out those observations, and you solve that for the ESL. You do the inversion for the ESL and for the the observations of the sum of the ESL and the isostatic terms and the tectonic terms, which I assume we've avoided from the slides. And then we do an inversion. And essentially what we do, in this case, a 3-layer model with the sphere upper mantle, lower mantle, and we define the parameter space in which we expect the parameters to lie, the thickness, upper mantle, lower mantle, and you essentially do a huge forward search in that space to get the best fitting model. And when you do that, the final result looks like that, a much more tightly bunched result. It looks similar to the observed one, but it has important differences. This is a comparison of the two. Here, one of the differences, if you just take the observations, you would conclude that sea levels were above present day value and then fell down to the present from about 7,000 years onwards. The ice volume, however, function shows that it will be slowly increasing over that period. And that signal there is simply the isostatic effects, the water loading effect on continental margins from the ice sheets. The other major difference is here, if you take the basic observations in that LGM, you conclude that sea level is about 125 meters below sea level, but that is not a global average. That is really determined by the distribution of the stations. It's very much a continental margin average from the distribution that we have. The ice volume number, if you want to convert the sea level to ice volume, you've got to go through this process, and then you get about 135 to 130, 33, 35 meters. A difference of about 15 meters, perhaps not very great, but that is equal to the amount of ice that was in the Scandinavian ice sheet, for example. So it's an important difference. So it's very important when you interpret sea level data in terms of ice volumes, what the ice sheets may have been doing, that you go through this process. You look quickly at a couple of the local solutions. Scandinavia, there we have a very good distribution of data. It took me several years to put that together, but the spatial distribution, the time distribution of that data is pretty good. And we have a good variation in the type of signal. And we use that variability to do the inversion. And I won't go through the details of that. I'll show the sort of the maps that sort of come out. For example, we produce ice sheets for that. Actually, I will go back just one step. It's from here. No, I won't do that. Sorry. I'm aware of the usual running out of time. This is leading into the glacial maximum. We actually have some resolution on that, the glacial maximum itself. And then this is at the time so-called younger dryas. And you see here some of these lakes that form, and we can actually predict how the water drains. In this case, these lakes connect up this way, and these lakes go that way. And this is the Baltic Ice Lake, which has left a beautiful shoreline all around the Baltic, which becomes one of our important observational constraints. And the sort of mantle rheology that comes out of this, as indicated here, the lower mantle viscosity poorly constrained, and we saw the reason for that. this intermediate size ice sheet simply doesn't stress the lower mantle sufficiently to give the resolution. And if you just look at the model, the best model, compare the predictions with the observations, we get pretty good agreement. Unfortunately, the North American situation, which is a much larger ice sheet, of course, it contributes about 80% to the total change in ice volume, is also not terribly well known. There's a problem with the data, there's not much of it, and it's not very accurate. A lot of it is limiting observations. All the black points, for example, all they give you are upper limits. They tell you that sea level has to be below that. And the green points are lower limits, tells you have to be above below that. And in many of these localities, it results in error bars of plus minus 50 meters, whereas Scandinavia is plus minus 1 or 2 meters for those periods. So the solution, unfortunately, is not going to be as good as we would like, and that's going to dominate our overall uncertainty of the whole GIA understanding. Sorry, not of the understanding, but of the GIA results. We start off, for example, with a typical model, the classic model of Benton and Hughes, which is a single ice sheet dome, about 3 kilometers thickness, quasi-parabolic type profiles radiating out from that. That's the sort of model you'll find in all your textbooks. And if I just take that model and solve in the inversion and try and find my best Earth model, then the residuals for the best Earth model look something like this. This is the observation and the prediction. If it was good, it's the Scandinavian one was after an adjustment. They should all fall on that line here. They're all over the place. But there's a lot of pattern in it. There's a group here from the Gulf and Barents, for example, where predictions greatly exceed the observations. There's patterns here in northern islands, for example, Hudson Bay, etc. So there are some very clear regional patterns, and we do regional solutions for each of those areas really to try and improve the ice sheet. And the models we finish up with look something like this. Rather than those parabolic models, we have models where we have multi-dome systems, one over to the west of Hudson Bay, there's one here, there's another one here, for example. And essentially different ice caps over the major islands, which are a thinner ice in the major straits. And this is one of our recent models with the different time steps. That's quite a different picture. And that now begins to look reasonably good when we compare it with the observations. But one of the important limitations that I should have pointed out, I'll do it on this one, was that this ice sheet is really restricted to this part. This is at 12,000 years ago. This is the underdryas one. Cordilleran ice sheet is gone from here. But most of the observations are from this area here. There's very few data. There are very few data from here, and most of it's not reliable because of the tectonics in that area. So if you ignore that problem in your inversions, there's a tendency to push ice into the middle where you've got no constraint on it. But we realized that these large lake systems that form the Lake Connell and the Lake Agassiz, and sorry, this is Lake Agassiz, the other lake here, so that's Agassiz, and never mind, I can't remember the other name. They have left very marked shorelines here, along here, along this section here, for example, along the coast there. And the change, and these are now no longer horizontal, so we use the gradients of the shorelines, and that enables us to provide a much better constraint of the ice sheet in these parts of the continent. So that's been a step forward, I think, in the North American modeling. And this is just an example of where we have the observations. They have the Alaska, that's the name I was trying to think of. We have the observations down here. We have this arm here. You see the different distances from the ice margin at that time, and that results in a spatial tilting of the lake. The Great Slave Lake, part of Lake, the old Lake Connell, we've been able to identify observations here that give us profiles across here, for example, and show the utility through time. So that becomes an important new data type. And putting all that together, we get this rather messy looking ice sheet, very different from the standard textbook ones, but which I think is actually correct, because we've tested this against the GPS results, and we indeed see the separate domes of uplifts in some of these areas that this model predicts, including up here. And this is still a work in progress. I think a lot needs to be done, but it's showing that we can do better than has been done up till now. So let me go skip. The final comparison between observations and predictions for North America, the best I can do at the moment, looks something like that. And it's a far cry from what we can do for Scandinavia. And we need to get data sets that will ultimately produce models that are as good as the European ones. So we do that. We've done similar analysis in the British Isles for the Alpine glaciers. We try to cobble together what information we have. Greenland is included in there. And we calculate the total amount of ice. We compare it with our far-field solution, 130 plus a little bit that we saw earlier. And we see this discrepancy. And that discrepancy we put into Antarctica. If I try to put it into the other northern hemisphere ice sheets, everything falls apart. So I think the answer is it has to be in Antarctica. And this picture shows that this is my far field solution for the ice volume function. This is my regional solution summed over the northern hemisphere ice sheets, and this is the difference. And if that's indeed Antarctica, what it tells me is that the Antarctic ice sheets start melting much later than the northern hemisphere. And I think physically what's happened here is that as the sea level rose due to the northern hemisphere melting, it destabilized the ice on the Antarctic shelf and then disintegrated. And then you had a fairly rapid decay of the Antarctic ice sheet, and in fact one that is continuing on into recent times. So let's assume that I've done everything correctly, and I can then begin to do some comparison between the various regions to see if it makes some sense. So if I assume that my ice sheets are okay, and then we look at the local inversions again. Now I've just summarized here the results for the 3-layer, and essentially North America, and Scandinavia, British Isles. That's one half-field solution is missing there, right? And essentially what we see is that lithospheric thicknesses, I'm a little bit flummoxed here, drop some. Okay, but let me just stay with this for a moment. We see that there's some suggestion of lithospheric thickness variations, although the ice sheets in the 2 ancient cratons are pretty consistent. The British Isles is quite a bit lower, and the far-field solution, which I was looking for, also is quite a bit lower. That will appear on the next slide. The upper mantle differences between the 3 continental areas, not terribly significant, except that Fennoscandia is generally lower than the other 2. And I think that's related to the fact that the resolution has a strong correlation between upper mantle and lower mantle viscosities. And again, for lower mantle only, The North American ice sheet gives us a reasonable sort of value. The Pan-Scandinavian ice sheet can be anywhere between over 1 order of magnitude, 2 times 10 to the 21 to 2 times 10 to the 22, and the British ice sheet gives us no constraint worth thinking about at all. If I do some sort of weighted mean, weighting them according to the area of each one, and then I get values that would something like that for the continental mantle. Not terribly different, but if I use these parameters for North America, I don't get a good North American solution. So I think there's a hint of significant variability in here. And the model tends to look something like this. This is the depth, the log of the viscosity, and this is the one I was looking for in the previous slide. We've got the North American solution in blue, the European solution in red, and the far field solution in the green out here. And the weighted mean of those three is the red area in here. And the question really, all thereabouts are 95% thereabouts. And the question really is it significant? Is this mean value going to be as good a predictor of what's happening today as models in which I have that variability? And the answer turns out to be no. The model with regional variability gives better explanation of the observations than one single model. The lithospheric variation is shown on this side here, and there is a tendency in North America, Pan-Scandinavia, British Isles, and then the far field ocean type environment of decreasing. Overlapping areas to some extent, so I don't have 100% confidence in this, but I think it's showing trends that are realistic, and I think that we need to pursue by trying to improve our databases primarily. I think that's the main stumbling block. For the far field, we've experimented a little bit in trying to see if there's a difference between the ocean island results and the continental margin results. One could anticipate some difference because the ocean islands sitting in the middle of an ocean environment, whereas the margin, there's the potential for flow between the ocean mantle and mantle beneath the continent. The numbers are not terribly convincing because the island data is very sparse, but that's what it produces. Here about the ocean island solution, the margin solution, the two lie outside each other's error bars, and the mean of all the data is actually split in the middle. Curiously, I don't think that the effective lithospheric thickness being greater here than here is surprising, because the ocean lithosphere is generally stronger material. Surprising to some extent is the fact that the mantle viscosity here is greater than the margin solution. And again, that's an issue I'm debating with Dan McKenzie. I think there is a good physical reason why that's happening, and that is, it's a complex one to explain, but the ocean islands, the water load component is not small. The dominant is essentially, if the island is a pinpoint, then the island just goes up and down to the seafloor and you get no relative change. So for very small islands, you would not see a relative sea level change. You would follow the geostatic or the ice volume equivalent sea level function. And as a result, we are seeing the effect of the residual effect of the response to the melting over the ice sheets. And you can see it in the following way. We have an ice sheet sitting here. As it melts, the crust underneath goes up and the crust on the outside goes down, because you get a bulge forming and that subsides. And That creates a space in the ocean basin, and water pours into it. So the ocean islands are seeing the collapse of that bulge, and that bulge is controlled more by continental mantle values. So my answer to this result is that if I'm going to do this calculation properly for the islands, I should calculate a glacial isostatic response to the ice component only using continental mantle material parameters, and the water load part I should use the ocean parameters. And when I do that, it goes for onto that curve. So there is a, yeah, sorry, I'll try and whip through it. We've looked at 5-layer models in which we have a most complex dependence in the upper mantle, and essentially there's absolutely no resolution in the upper mantle for the large ice sheets. Only for the British ice sheet here do we see some resolution here going from a low value in the uppermost part from basically between 200 and higher value here, and out here the resolution becomes very poor. So that's consistent, in fact, with our very early solution. We see only for that ice sheet. So what I can do is I can introduce a model in which I put those layers in and use these parameters, and provided that my parameters, the weight averages, are equal to my far-field solutions, I could use that model as an equivalent one. Let me skip through that. The other one we've looked at a bit more carefully is what happens in the lower mantle, and there's a lot of recent literature that suggests that there's been an increase in mantle viscosity at about 1,000, 1,200 kilometers, and I think indeed we see that. I keep my upper mantle at the earlier determined values. Now I'm going to vary that as well. And I just introduce an intermediate layer and I calculate the viscosities for those. And we see some suggestion for a variation in these two ice sheets, and in particular what it does for Panascandia, it brings the numbers more in line with the other regions. So I think there's some potential to make some comments about that intermediate layer boundary. I think it's probably a real thing. I can't say if it's at 1,000 kilometers or 1,200 or possibly 1,500 kilometers, but something is increasing there. So let me just go straight back to the summary. Where we stand today, the 3-layer models, I think, are largely adequate for everything that most of us want to do when we look at corrections to for other purposes. They're not sufficient for understanding the actual mantle viscosity. And I think we can predict the present-day GIA rates through GPS measurements, for example, from sites away from the ice sheets to within about 10%. And we can also do that for the ocean islands within about 10% using this hybrid model that I just very briefly sketched out. For the glaciated regions, we also have reasonable predictive capability, not quite as good as for the far field, because the uncertainties in our final ice sheet are still larger than I would like them to be, but we can do a pretty good job there. And I think on the basis of that, we can sort of essentially extrapolate to all of the far field areas around the world and all of the former glaciated areas where the glaciation occurred on old cratons. And it leaves the question of what happens in the intermediate sites, in the Mediterranean for such an intermediate site. So at the moment, based simply what I've said so far, I can't do a satisfactory prediction here, but I think there are two avenues. One is this hybrid solution that I indicated. We use the water loading, the effect of the water change primarily in the Mediterranean basin. We use the parameters for continental margins, global solutions, and for the ice part, we use the mantle parameters beneath Scandinavia. And that seems to work. Or I can concoct some sort of average of the two values and just use that with the three-layer models. And that's what we are trying to do at the moment with the archaeological data. And the very preliminary solution we got a day or two ago suggests that this sort of approach works quite well. We've taken the archaeological data, done a preliminary inversion, and we're getting values in between the two, and it all looks quite promising. For Antarctica and far southern latitudes, I decline to make predictions because I think they are totally uncertain. So far southern being below about 60 degrees south. So I think that's roughly where we stand today. There's a lot of work still to be done, but I think we've made some progress. And I'm hoping that by the time I leave here, we'll have made a bit more progress. For those of you who remain, thank you. Apologies for going over time as usual.
So thank you, Kurt, for a very interesting seminar. So, if there are any questions? No questions?
Well, I have plenty of questions, but mainly, I mean, the general view is very helpful. But as you know, my main interest is in the low velocity layer, and which is practically invisible to
well, that's one of the conclusions.
Yes.
Not really see it. We have to ask ourselves, how low can it be before we begin to see it?
Yes.
And that's exactly the argument it's trying to do that.
So using the averages, which are very helpful for the entire thickness of the upper and lower mantle, that thin layers are practically.
But I'll emphasize this here because there are people who are publishing results for very thin layers from TLA modeling in Mantle. The rest of the model comes under the but perhaps we can have some intelligence.
Yes.
Could just concerning our common work in these days, what do you expect from the observation in the Mediterranean for your modeling?
Yeah. The Mediterranean.
Can you please give microphone for the people?
Sorry. The essential problem with the Mediterranean, of course, is that it's so contaminated by tectonics. I mean, that's the real crunch here. How can we say anything about one component when the other component of probably equal importance is less certain? So one of the important things that we do here is that we look carefully at the geological evidence, and this is where Fabrizio comes in, particularly with the last interglacial shorelines. If we find these within a few meters of present-day sea level or whatever our model predicts them to be, then we assume that those areas have probably have been relatively stable, and we put largely use it. We put certain error bars on that. Now, exceptions, of course, occur where the land has been going up and down, around Naples, for example. But we assume that those areas are known from other considerations, and we stay away from them. So we finish up with a number of observations around the Mediterranean that look relatively stable in the sense of minimal vertical components. It doesn't mean there may well be horizontal movements, of course, and have been, but the vertical components are very small. So we use the observations from those areas and do the inversion for the Earth model parameters. And that's the stage that we've just started doing the last few days. And the preliminary solutions are finding values that are between, as I said, the ocean and the continental values, which is good. And the analysis shows that I think we have resolution there. And so what we need to do next is to do that inversion properly using a much larger data set than I've been able to do here so far. The other thing we want to do is look at the geological data from the same localities that go further back in time and do a separate inversion there to see if the same Earth model more or less comes out from that. And if that's the case, then I think we will have something that's going to be useful for predictive work. At the moment, what we've done with this preliminary solution, we do predictions for all of the sites where we have, in this case, archaeological evidence, and compare that with the observations. And we use the differences to see whether there's been tectonic uplifts or subsidence, and we compare that with our geological knowledge to see if that agrees. And so far, it looks encouraging. We see the and that's really all I can say so far about where we stand. But it's all. So I think at the end of the day, we should have a model that will give a good representation of the GIA contribution to land uplift or subsidence and to sea level change that can be used for predictive purposes for stable areas. And then the differences between those and data from unstable areas should provide us with a tectonic map of uplift since in the last 2,000 years, something like that. And then if we have that, we can then begin to reconstruct what landscapes along the coastlines look like. That's the sort of the broad aim of the exercise. And I emphasize this is very much a three-way exercise between the geological, the archaeological, and geodetic work, and my own sort of modeling with some of my components only.
So, any other questions?
Hi, I'm Giancarlo Scavera.
Please, can you speak to the microphone? Is possible? No. Okay.
I'm a follower of
Maybe
You just have to speak loudly. Sorry.
well, for people attending the seminar from
If anybody
I am a follower of expanding earth.
Yes.
And there are effects. Have you considered that there are possible effects of the expansion of the globe on the load of the isostatic load? Because if the general globe curvature is decreasing with the expansion, and if the ancient curvature of the continental lithospheric fragment tends to conserve, the contrast between the conserved curvature and the decreasing curvature can introduce additional load.
Yeah. I mean, it's something coming from the southern hemisphere and having been subjected to Sam Carey's views on expanding Earth. I'm familiar with the arguments. And I have, in part of my earlier career, when I was looking at the rotation of the Earth, because we have these paleo indicators of what the Earth's rotation was like in the past. And from that, we've been able to get estimates of limits on the maximum amount of expansion that may have occurred. And generally, they are, I think, too low to compare to the sort of processes that I'm looking at here. The other observation we have is the geodetic data. There is no evidence of measurable change in the Earth's radius, for example, or in the Earth's flattening that cannot be explained by normal geophysical processes without requiring a global average. There's nothing in the data, the geodetic data, that says that there is a expansion at a measurable rate. Now, it may be that the rates are too small. The measurable rate's probably only 1/10 of a millimeter per year. And I suspect I think you're talking about something that's going to be smaller than that. So I think if it occurs, I think it will be masked by these larger processes.
But the geodetic measurements are for the actual time.
Yeah, they're just for the reason. So
We cannot
20, the period is too short to do that. But the geological data, the rotational data is probably the best constraint. And you know, there's a long, famous debate between Runcorn and who's the other Englishman? Littleton. I can't recall, but that business has been explored in quite a lot of detail, and I addressed it, I think, if I remember correctly, in my rotation book, but that goes back 30 years. I can't be expected to remember what I wrote 30 years ago. But it's an interesting point, and it's something that one has to keep in the back of one's mind. But I think at the moment, it's below the noise level of what we are seeing in the data.
I can provide you with the print.
Yeah.
That there are some arguments about expanding Earth.
Yes. Yeah. I sort of have followed that literature in the past. I haven't looked at it in recent years, but yeah. Right.
Okay, so thank you, Kurt, for your question segment.
Okay.
I was many years ago. No, but
Yeah.
the short time.
Yes. Okay. Right. Yes.
And I translated in Italian the book expanding the Earth. Yeah. I follow it working in retired now. Working. Okay.
Okay. Good.
Okay, sure.
Yeah.
You are this way.
No, I've got that one.
Okay. Okay, we want to raise the PowerPoint. You want to leave here or you want to raise? Okay, okay. Okay, now.